In this lecture, we're going to talk about clustered or dependent data. And broadly speaking, we're going to consider a few different things in this lecture. So what are the consequences for our models of having dependent data? When we have dependent data, we can make hypotheses about within and between unit effects and what are the consequences of this choice. And when we use unit effects to deal with dependent data, are we better off using fixed or random effects? And we're going to talk about all of these things in a lot more detail below. But first, let's talk a little bit about what we mean by dependent data. Here, dependent data is really a sort of synonym for either clustered data or multi-level data. Sometimes we could use it to mean time series cross-sectional data. But in any event, they have the feature that we have observations at different levels of aggregation. So one example would be, and sort of the canonical example is children in classrooms in schools, which also are nested in districts and then also in states or provinces. And it might be that there are attributes of all of those levels that are important, right? That the children have attributes that might explain their performance, but they all share a common teacher, right? Maybe there are attributes of the teacher that explain their performance as well. All those teachers are nested in one school, or a lot of teachers are nested in one school, and maybe there are attributes about the school that are important for understanding performance. Right? Maybe it's about resources in the school or its geographical location. Schools are nested in districts, right? Same thing. Maybe there are attributes of the district that matters to predicting performance, and so on and so on. So the idea is that we could have information that existed for all these different levels, right? We have information about the children, information about the classrooms that they're in, the schools that those classrooms are in, and the districts those schools are in. Right, and that the fact that we've got information that exists at different levels of aggregation poses some challenges for our modeling. But I should say, just to be clear, the outcome that we're explaining is an outcome at the lowest level, right, at the children level. So here we would have a different outcome for every child, but the information that we would have about the child, some would be about the children themselves, and some would be about their environments. Another good example is voters in political ridings. So there might be something about the riding itself that would explain vote on top of the characteristics of the voters themselves. And we might have democracy measured at different years within each country, right? In all of these, a prominent feature is that the observations can be thought of as nested in groups. And like we talked about, these groups can have attributes of their own that we might care about or that might be useful for helping us predict some outcome at the individual or lowest observation level. So recall that OLS assumes each observation is independent of the others. Or more specifically, that the error term, or equivalently the Y values in repeated sampling, are independent of each other. We didn't spend a lot of time belaboring the assumptions of the model, but this is a pretty important one, and this one gives rise to all sorts of potential problems, some of which we'll talk about and some of which we won't. We know that this assumption of independence is rarely perfect, but in practice, a random sample from a large population provides a close approximation. If this independence assumption is violated, OLS is no longer the optimal estimation method, as standard errors are biased towards zero. Right, so the problem here is not necessarily bias in the parameters, although we could sort of think about it like that in some cases. The real problem is that the standard errors are wrong. So if we think about what happens when we have multi-level data in thinking about the calculation of standard errors, the standard error of a model coefficient is the standard error of the residuals divided by the sum squared mean differences in x, the standard error of the residuals, so this is the square root of the sum of ei minus e bar squared over n minus k minus 1. So we talked about this a little bit before. And this really equals, if we did a little bit of math and rearranged, the standard deviation of y over the standard deviation in x multiplied by the square root of 1 over the minus the squared correlation between x and y over n minus 2. So here you can see actually in this term, and here, n is an important piece of information, right? The sample size. When the observations are not independent, the effective sample size is smaller than what we observe, and thus we have to adjust the standard errors or they'll be biased downwards. Unit effects are one way that we can account for this non-independence. One way that we can think of these are essentially dummy variables for all but one value of an identifier variable, so like country or riding or province. This dummy variable approach, which we'll talk about more in a minute, is called the fixed effect approach. These can help us better understand what the other parameters in the model mean, so I'll talk more about that later. And there are competing ways of doing this, which we'll investigate below. So the dummy variable approach is one way, but there are other ways too. But most importantly, unit effects are meant to capture unobserved heterogeneity. So remember, we said before, maybe there are things about the classrooms that matter, right? And it could be that we could measure some of those things, right? Maybe we know how long the teacher in the classroom has been teaching, how long that person has been teaching that grade. So there are things that we could measure that wouldn't be that problematic. It should be a T. But there are lots of things that we can't measure, right? We can't really measure in a meaningful way across a lot of contexts, sort of teacher quality. Right? There are other things like similar laws, administrative structures, social policies, and norms that might affect the outcome that we either can't or at least we didn't measure. And so unit effects are a way of capturing this heterogeneity, the variance at different levels of aggregation without having to measure all of those things. So on the one hand, this does provide a statistical solution to this problem, right? We are able to account for the non-independence. But I just want to make clear that using these doesn't actually give us any insight to what it is about the units that make them interestingly different, right? So it solves a statistical problem, but it doesn't usually give us much substantive insight. So to move away from the abstraction a little bit, I want to think about a particular hypothetical data problem, and think about what sorts of things we might want to be able to learn from these data. So here we've got data on 5 different groups, right? So each symbol type, we've got circles, triangles, pluses, X's, and diamonds. These each represent different groups. Right, so these all represent different groups. So one thing that we might want to know is what's the relationship between X and Y within each group? right? And that's what these positive sloped lines tell us. So that's one thing that we might want to know. Another thing that we might be interested in is if we calculated the mean of x and y for each of these points, we might want to know at the group level, how does the mean of x relate to the mean of y? Right, so these things, these lines, are called the within unit effects, and this line is called the between. The between unit effect. So you'll see that there are actually really strong, basically perfect relationships within and between units. Right? So there's a perfect within unit fit, and there's a perfect between unit fit. This line is the OLS line that we would fit if we didn't know that the data were grouped this way and we weren't paying attention to thinking about between and within unit effects. So you can see that this effect, the OLS line, is some compromise between the between and within unit effects, right? It's negative, but it's not as steeply negative as the between unit effect. The bad thing about this compromise is that it's not one that we have any control over. We don't know how much of the between and how much of the within unit effect we're getting in each OLS outcome. So what I really wanted to say here is that just doing OLS on these grouped data is going to give us the wrong answer, right? There are maybe different kinds of right answers that we would be looking for. Maybe we're interested in between, or maybe we're interested in within effects. But regardless of which one of those things we might be interested in, the OLS answer is going to be wrong. So the two estimators, and we could make either of these estimators happen just by transforming the data a little bit. So the between estimator takes the mean of y for each group and regresses that on the mean of the x's for each group, right? And the coefficients that we get from this model. So this is an OLS, but what we've done is we've imposed a certain kind of effect on the model, right? We've asked it to tell us something about the between unit effects. If we wanted to know the within unit effect or the within group effect, what we would do is we would take these group means and we would subtract the individual observations of y and x from their group means. Then on these variables that have the group means subtracted, we could run an OLS, and that would give us the within effect, right? So that would actually allow us to evaluate the within unit effects. So thinking back to the graph that we saw before that had those three different effects, the between unit effect was basically this one. 8 minus 1 times the group mean of x was the predicted group mean of y. So the coefficient for the between effect was -1. And the coefficient for the within effect was +1. Right, and we saw that the coefficient for the just regular OLS without paying attention to grouping at all was -0.33. The neat thing is that with a multi-level model, we can actually recover all of these things. right, we can recover both the between effect and the within effect. And that makes it pretty well suited to sort of what we're trying to do in general here. We're going to talk about relatively simple multi-level models here. The simple part being that we're really only interested in what we would call random intercepts or varying intercepts. So in this model, we allow the intercept of the model to be different for each group, but we're forcing the coefficient for x to be the same. Here, we're actually modeling this random intercept, this intercept that differs for every observation. And we're modeling that as a mean, right, a single parameter, plus a residual. Right, so this random intercept, this intercept that varies from group to group, is a function of an overall mean parameter, and then a residual, something that gives us differences from that mean. And if we plug this new equation, or this B0 equation in for B0, we'd get an equation that looks like this. Just sort of by way of information, this we would call the structural. This we would generally call the structural form of the equation, and this we would call the reduced form. Right? They're both telling us the same thing, but they present the information in slightly different ways. So now, in one way of thinking about this, both of these, the U0Js and the RIJs, are both residuals. Right? They're just residuals at different levels. The Rij are individual or level 1 residuals, and the U0Js are group level, or usually what we would call level 2 residuals. But it's important to note that neither of those residuals is directly observed, right? We can recover them from the model in various ways, but neither of those terms is actually observed in our model. There are two different ways for us to think of the U0Js. We could think of them as fixed, in which case we would actually estimate a different parameter for all but one of those. We'd leave one out for identification, just like we would for any categorical variable. So basically, we'd take our identifier variable, classroom or country or province or riding, we turn it into a factor, and we just include that factor in the model. And that may, in fact, generate lots of parameters, but that's okay. One thing to note is if we think of these as fixed, these group level parameters are by definition going to be perfectly collinear with any explanatory variable that only varies by group. So let's say we put fixed effects for provinces in, right? We couldn't then include information that only varies at the province level, like the province's GDP, or some policy difference that only varies across provinces and not within. Right? Those things, we couldn't estimate all of those at the same time. If we think of the U0Js as random, then we think of them basically as group residuals, like we talked about on the last slide. This way is appropriate if the groups are considered exchangeable, that is, they're all drawn from a population of groups. This would really make sense in the classroom, in school setting, right? There are loads and loads of classrooms out there, and maybe we have a sample of those. It sort of makes a bit less sense thinking about it this way in the political ridings example, because usually we would have all of them or most of them. But even if that sort of interpretation is strained a little bit, we can still use these models to good effect. When we think about the unit effects as random, there's one parameter associated with the groups in this model, and that's the variance of the group effect. Right, so this variance is actually the parameter that we really care about, and I'll show you an example of what that looks like later on and how we can think about that term. But that tells us essentially how variable are those group intercepts around the mean. If they're really variable, it means that there are actually really big differences in sort of baseline outcome as we move from one group to another, and if that variance is really small, it means that there aren't. There's loads of advice out there about whether to use fixed or random effects. So we'll go through a sort of few pieces of conventional wisdom, although none of these are sort of hard and fast rules. If the groups are of interest to the research and researchers want to make inferences about the differences between groups, we should use fixed effects. Well, this is true because we generally don't have, because we're not estimating the unit effects directly when they're random, we can't do tests of differences between them. If the groups are considered to be sampled from a population of groups and we want to make inferences pertaining to that population, we should use random effects. And it's because basically the variance term tells us the variance across all groups, the known ones and the unknown ones. Fixed effects only can really tell us about the unit effects for the units that we observe. If we want to test proportions, if we want to test propositions about the effects of group level variables, then random coefficient should be used. There is a piece by Thomas Plumper and Vera Troger, who are political scientists, that talks about a way to do both things, to make group level tests even with fixed effects, but that paper hasn't really caught on that much. If group sizes are small, then random effects can help leverage strengths across the groups. And random effect models work best when the assumption of approximate normality of these residuals and the level 2 and the level 1 residuals holds. We're always making normality assumptions about the level 1 residuals. So that's these guys here. When we have random effects, we're also making normality assumptions about the level 2 residuals as well. So I had you read a piece by Bell and Jones, and they make the following suggestion. In any model, we should actually use both the within and between transformations to identify the different effects in a multi-level model setting. So in a multi-level model, we're sort of uniquely positioned to be able to account for and describe both the within and the between unit effects. There was also a paper about this thing by Brandon Bartels that I'm not sure ever got published, but it was an interesting paper just the same about using these kinds of models in the time series cross-sectional setting. But he made basically the same argument that by calculating doing the between and within transformations for all the variables, you're actually accounting for all of the kinds of effects that you could get. So I want to move to talking about a more concrete example now. So here we've got data that are a subset from the 1997 British election survey. This used a multi-stage sample where first parliamentary constituencies were randomly selected and then voters within those constituencies were randomly selected. So we have 2,141 voters nested in 136 different constituencies. We're going to try to explain left-right self-placement as a function of a bunch of other variables. Note that some of these, right, well, one of these in particular, the percentage of professionals in the constituency, is a variable that's at the constituency level, right? There is no individual level analog for that, right? So we have one variable that's at a higher level of aggregation. I have age, sex, degree, and income. That are all at the individual level, and PANO is our identifier, right? That identifies the group. So our hypotheses are these. Household income affects attitudes, so the richer one is, the more right-wing on average their attitudes will be. The relationship will differ depending on the area in which one lives. If they live in rich constituencies, they'll be more likely to hold a right-wing attitude regardless of their own wealth. So this is really that. So the first one is really a within effect. And the second one is a between effect. And we're going to evaluate whether the intercept varies across constituencies. We're actually not going to do this second part. Although we could, these models allow us to evaluate whether the slope of income varies as well, but we're going to leave that be for now. So multi-level regression models, which you might also hear called hierarchical models or hierarchical linear models or mixed effects models, all of those generally mean the same sort of thing. These allow us to learn about within and between unit effects. So here, we have this same sort of setup that we did before. So this is just sort of replicating that equation that we saw on a previous slide, along with what all of the parameters in that equation mean. So I don't know why that didn't print, but LME4 is the package that we're using, which you'll have to install probably. And the function that we're using here is called lmer for linear mixed effects regression. I also did in the code for the class, actually here, let me just go grab that. So this code file is on the website, the OWL site for the course. There's a function in there called make between data. And what that function does, you can see it here, is you put in a formula, the same formula that you would use in your model, and it takes those variables and makes both the between and within transformations. You also have to give it the data and the group identifier. And it makes variables that have an underscore B for between and an underscore W for within. So even though you don't see all of the steps in the slides, all of the steps exist in the R code file that you can see on the OWL site. So the big difference in the formula is that in addition to all of the variables, we add this in parentheses, 1, the little pipe character, and whatever the group variable is. For me, the little pipe thing on my laptop is shift and right above the return key. But depending on your layout, it might be in some place different. We can summarize this model, and there are a few things that we need to look at. So here we get, for all of these individual level variables, we get both between and within unit effects. And you can see sometimes they're pretty close to the same, right? So the between and within unit effects of age are actually pretty close. 0.026 versus 0.04. The between and within unit effects for gender are really quite different though, right? 1.26 for the between effect and 0.14 for the within effect. Now, it's important to note that this, what looks like a really big difference, is likely a function of the fact that they have, those variables have quite different variances, right? So where the within effect starts out with zeros and ones, right? Although we take away the group means, the group means of gender are probably pretty close to around the 0.5 mark. So there's not probably a lot of variance on the group means. There'll be a lot more variance on the within effects. So that's maybe not an entirely surprising result. The other thing to note is that the percentage of professionals only gets a between effect because it's a second level variable, right? It doesn't have any individual level variation. The other thing we need to think or look at is the variance, or maybe better, the standard deviation of the random effects. So this is the standard deviation of Rij that we looked at before, and this is the standard deviation of U0j that we had talked about before. And we can sort of compare those two figures because they are both residuals. And to the extent that the group level residual, the standard deviation of the U0j's, is small, it would mean that maybe we don't need the random effects as much. But it doesn't hurt to have them in there, and it doesn't really impair the way that we evaluate the model in any way. So unless they're really, really close to zero, there's not a good reason to leave them out. The other thing you'll notice is that there are no p-values here, right? We get t-statistics, and you wonder, well, were they just lazy, right? When they wrote the code for this function, did they just not put the p-values in because they were either lazy, or they just assumed that everybody could actually go out and find the p-value for a t-statistic? And as it turns out, that's not exactly the reason why we don't have them. And we'll come back to this in a little bit as well. So the coefficients that we saw above, the income underscore W term suggests that within groups, as individuals have higher levels of income, they have more right-wing attitudes. And the between unit effect suggests that the more affluent constituencies, as measured by their mean income, tend to be more right-wing. So on the whole, richer places have more right-wing attitudes. So there is a positive within effect and a positive between effect. So what if we wanted to actually look at these random effect terms, at these 0 U0Js? How would we actually get them? Well, luckily R does this for us. But there's actually some interesting stuff in at least a simplified version of how these are calculated. So these are calculated for a model with no independent variables, but the sort of general idea is pretty much the same. So there are two components of these. There's what we might call the grand mean of y. So this would be the mean of y across all observations, independent of the grouping. And this is the group mean of y. You can see that these random intercepts are a function of these two different pieces of information. The weight on each piece, right, lambda here and 1 minus lambda here, lambda is again a function of a couple of different things, right? So this is the this is the variance of U0J. This is the variance of Rij. And this is the number of observations in group J. So basically, one way we can think about this is as the number of observations gets really small, right? Let me make sure this bigger. So as n sub j gets small, sigma squared over n sub j gets big. And as this gets big, the denominator of that fraction gets bigger, and then lambda sub j will get small. Right here, it's probably useful to note that lambda is a probability, and so we can think about lambda as a probability, so it's bounded between 0 and 1. Right, so when we have not that much information in each group, or for a group that doesn't have much information, if lambda is small, then most of the random effect or unit effect comes from the grand mean. As n gets really big, as n sub j gets big, then sigma squared over n sub j gets small, and then lambda j gets big. Right, and so as lambda j gets big, that is, if we have a lot of information in the group, we have a lot of observations in the group, then the random effect is mostly the group's effect. So when we talked earlier, just briefly, about being able to borrow strength when we have groups with very different numbers of observations, this is what we mean. That depending on the group size, we can get estimates that are either closer to the group mean or closer to the grand mean. There's a function called RANEF. This is also in the LME4 package, and it allows you to generate these empirical base estimates of the random effects. So these are of the U0Js. Right, so if you wanted to look at them, you could. If you wanted to evaluate the normality assumption, You kind of could, right? You could at least make a guess at it. So that's interesting. So there's actually has been a lively discussion on the R mailing listserv that dates back, almost 15 years at this point, about why there aren't p-values in the output of the lmer function. And the person who wrote the function makes a pretty compelling argument for not having p-values there. And it's basically because we don't really know what the right degrees of freedom are for a particular variable, right? Variables that are measured at different levels have different degrees of freedom. All of that notwithstanding, it's still nice to have a p-value for your variables. And so there is a function. There are actually several functions in R that will do this, but this is the one that I think maybe makes the most sense. It's in the lmer test function, and you have to update your model, which essentially estimates it with a different function in this case after you load the lmer test package. And then you can use the little a ANOVA. Now, we have talked a lot about not using little a ANOVA on a single model. But it tells us right here, and we didn't actually sort of talk about the typologies of ANOVA, but that it's using type 3 sums of squares, which is basically what you would get if you just did a regression model. Right, and looked at the regression output, that would give you the type 3 sums of squares and their p-values. So, in any event, when you're using the lmer function that you estimate from the lmer test package, using the little a ANOVA is okay. What's interesting here is that you get the degrees of freedom for each variable. And so you'll notice for all of the between effects, we get degrees of freedom that are on the order of about as many groups as we have. We got 136 groups. Sometimes a little smaller, sometimes a little more, but it does give us about the right number. We also, from that, get what are approximately right p-values, right? Because they're based on what is a good guess at the right degrees of freedom. So here we can use these p-values and sort of flags for significance in our regression output if we wanted to. So if you were making a table of these results for a paper, you'd put the coefficients in and the standard errors, and you could use these p-values to identify significant or not significant ones. And you'd want to make sure that you identified the source here, right? How you came up with those values. We could test hypotheses between two variables or two effects. So if we wanted to test the within versus between effect, we could do that with the linear hypothesis function. And in these models, the effects functions work. And so this is probably your best bet at trying to evaluate what effects look like in these models, especially if you have some nonlinearities and the like. The component plus residual plot function doesn't work because of the more complicated nature of the residuals. You could sort of hack one of these together yourself if you wanted to, but with between and within effects in it, it becomes a little bit more challenging. The DA-MISC tools don't work here, in part because of the more complicated nature of interactions that we didn't really discuss in this model, but that makes them a little bit less amenable here. to these kind of functions. And if you wanted to apply this mixed models or multi-level model framework to other kinds of models that we've talked about, there are lots of options out there. So GLMER is also, this is in the LME4 package, and that gives you access to all of the multi-level GLMs. So with the same families that we could use when we estimated the GLM function. There's a function called CLM that's in the package called Ordinal that does multi-level ordered logit and probit models. And there's a function BRM in the BRMS package that does multi-level multinomial logit models. The estimation framework in the BRM function is Bayesian and not frequentist like the ones that we've been talking about. But if you're really in a jam, you could use that function to estimate a multi-level multinomial model as well. Again, just like before, what you would present with these models is all of the things that you would present for any model. You'd give the coefficients, the standard errors, some indication of significance probably. Model fit is a little bit more difficult here because the R squared is more complicated. So you might not spend a lot of time talking about model fit, but you would definitely put in what the residual variances are, the variance of the individual level or level 1 residuals, and also the variance of the level 2 residuals. Those are important pieces of the output for these kinds of models. And then you could use any of the effects functions to help figure out what the effects of variables are and present the relevant things from there. So with that, there's one more video that will be coming shortly about multiple imputation and missing data, and you can look for that soon.